Let's begin by discussing schema evolution and focus on backward compatibility. In the world of data, schema changes are inevitable, but we need to ensure that these changes don't break existing consumers. With backward compatibility, we ensure that older consumers can still read messages that were produced with newer versions of the schema. Let's imagine a scenario where we have a producer sending data using schema v1. The consumers are still using this schema. Now we update our schema to schema v2 and add a new optional field. The beauty of backward compatibility is that consumers still using schema v1 should be able to read messages produced with schema v2 without breaking the system. We run through this process with Avro CLI, which help us understand what happens behind the scenes when we serialize and deserialize data. We'll use Avro for this example, but the concept we are demonstrating here apply to other formats like JSON and protobuf as well. Let's begin by exploring Avro, a powerful serialization framework designed for efficient data exchange. Here's why it's popular. First, Avro provides compact binary serialization, which is much smaller than text-based formats like JSON or XML. This makes it ideal for big data pipelines. Next, it's supported by Schema Registry, a centralized service for managing schemas in Kafka. This simplifies how producers and consumers communicate by ensuring they are always schema compatible. Finally, Avro design is well suited for big data pipelines, especially in distributed systems where performance and consistency are critical. First, let's set up Avro CLI. If you don't have it yet, you can download it from the Apache Avro downloads page. Simply download the latest Avro Tools jar file and move it to a directory in your path. You can use wget to download the files. Once downloaded, we can check if it's working by running the Java command. Let's start by defining our schema in a file named payment.avsc. This schema acts as the blueprint for our data, specifying what fields the data will have and their data types. In this case, we are defining a payment record with 3 fields: user ID as an integer, amount as a float, and currency as a string. This schema ensures consistency across all data points, meaning every payment record will follow this exact structure. Once the schema is ready, the next step is to serialize the data using the Avro CLI. Serialization is the process of converting our human-readable data into a compact binary format, which is smaller and faster to process. This serialized data is what gets stored in file or transmitted over networks. By saving the data in Avro format, 2 key advantages: the data becomes smaller, saving storage space, and it is self-describing, meaning the data is embedded in the file. This makes it much easier to share and interpret the data later. Serialization is where we take raw data and encode it into Avro format based on the schema. First, we create a JSON file with some sample payment data with the echo command. The command writes the JSON object into a file named payment.json. This file represents a single payment record, following the schema we defined earlier. Then, using the Avro CLI, we convert this JSON into Avro format. The result is a binary file that includes both the schema and the data. The Java-jar Avro tools to run the Avro CLI tool. From JSON flag is the command to convert JSON into Avro format. --schema-file payment.avsc specifies the schema file to be used for serialization. Lastly, payment.json is the input file containing the raw payment data we created earlier. Inspecting the binary file is an important step to ensure everything is in order. We can use tools like hexdump to peek inside the file and confirm that the schema and the data are correctly serialized. This step is particularly useful for debugging or verifying that the process works as intended. This command will output a hexdump of the Avro file, where you can see the binary representation of both the schema and data. Deserialization is essentially the reverse of serialization. Here we take the Avro file and convert it back into a readable JSON format. This demonstrates that our data can move seamlessly between formats, a feature critical for data pipelines where data is stored in one format and consumed in another. To deserialize the data, we use the Avro serialize tool once again. This time we use the toJSON command to convert the binary Avro data back into JSON format. Here we are using the same java-jar Avro tools again. toJSON is the command to convert Avro data into JSON format. --reader schema file payment.avsc specify the schema that should be used for reading the data. This schema should match the one used for serialization. After running the command, you should see the same following output: user ID 1, amount 100, currency is USD. This is the JSON representation of the payment record that was originally serialized into Avro format. The data is now back in a readable format, ready to be processed or shared. Using Avro with Kafka brings even more efficiency and consistency to your data pipeline. Here's how it works. First, we define our schema and register it with the schema registry. The registry acts as a centralized repository, ensuring that producers and consumers use the correct schema versions. When a producer sends a message, it does not include the entire schema. Instead, it sends a schema ID, which is a lightweight reference to the schema stored in the registry. The actual message consists of three parts. 1. A magic pi to indicate that the message uses Avro serialization. 2. The schema ID to identify the schema in the registry. 3. The serialized data itself. Kafka brokers don't interact with the schema, they simply store and forward the message as is. When a consumer receives the message, it fetches the schema using the schema ID, deserializes the data, and reconstructs it into its original format. This separation of schema management and data storage ensures that your Kafka system remains lightweight while still benefiting from schema validation. Let's recap the key differences and similarity between using the Avro CLI and Kafka with schema registry. We'll cover each step side by side. For step 1, in both approaches, the process begins with defining a schema. For CLI, we set the schema locally in a .avsc file. For Kafka, instead of a local file, the schema is directly registered with the schema registry. This centralizes the schema management and makes it accessible for producers and consumers. Next, we serialize data using the schema. For CLI, we manually create a JSON file with sample data and convert it into Avro binary format using the Avro CLI. The result is a binary file payment.avro, which embeds both the schema and the data. For Kafka, the producer performs serialization automatically. It uses the schema from the schema registry, assigns a schema ID, and adds metadata to the message. This reduces the size of each message sent to Kafka, since the schema isn't embedded repeatedly. Debugging or verifying the data is an optional but useful step. For CLI, we can inspect the Avro binary file locally with tools like Hexdump to ensure it includes both schema and data. For Kafka, brokers don't inspect or modify messages, they simply store and forward the data as is. Finally, the data is deserialized back to its original format. For CLI, we use the Avro CLI to convert the binary Avro file back to JSON. For Kafka, the consumer retrieves the schema ID from the message, fetches the corresponding schema from the schema registry, and deserializes the data seamlessly. Schema evolution is about handling changes to your data structure over time without breaking existing applications. Imagine you need to add a new field to your schema. This happens often as your business requirements grow. For example, we might add a payment method field to your payment schema. The key is to make these changes in a way that is compatible with existing consumers. Backward compatibility means that older consumers can still read the data, even if it includes a new field. For example, if we add an optional field, older consumers will simply ignore it. However, some changes like removing a field or changing its type can cause compatibility issues. These are known as breaking changes. They require careful handling to avoid disruptions in your data pipeline. Let's walk through a successful schema evolution example. Initially, we have a schema with fields for user ID, amount, and currency. Later, we decide to add a new optional field, payment method. This change is backward compatible, meaning older consumers that don't know about payment method can still read the data without any issues. How do you add this field without breaking everything? Backward compatibility is the key. By making payment method optional, older consumers won't complain. They will just skip it. This ensures your system stays robust even as it grows. Let's see exactly how this works step by step. Let's walk through these steps together. First, the producer is still using the original schema. It's producing events with the fields we defined earlier. Nothing has changed on the producer side yet. Next, we publish a new schema. This new version includes a nullable field, which means it can safely be missing in older messages. Now the consumer restarts. When it comes back up, it fetches the latest schema from the registry. That's the one with the new nullable field. Here is the important part. The consumer can now use the new schema to read older messages. Since the older events don't contain the new field, the consumer simply treats it as a null or uses the default value. First, let me show you the original schema. It's simple but gets the job done. It defines three fields: user ID, an integer representing the user, unique identifier, amount, a float for the transaction amount, currency, a string like USD. Here's how this schema looks in JSON. Now comes the update. Let's add the new field payment method, but in a backward compatible way. This field will be nullable, meaning it can have a value like credit card or P-note. This ensures older consumers don't brag. They will see note and move on happily. Here's the updated schema. Notice the new field definition. By setting a default value of null, we ensure compatibility with existing data. This simple change makes the schema ready for the future without disrupting the present. Let's stick with the producer using the original schema for now. Imagine we have a payment record with these details. User ID 1, amount 100. The currency is USD. The key takeaway here is that the producer doesn't know about payment method yet. It just works as usual. Now let's switch to the consumer. It has been updated to use the new schema by restarting the consumer application. It checks Schema Registry for new changes and gets updated to the new schema. When it reads the older messages serialized with the original schema, what happens to payment method? It gets the default value of null. Let's take a look at the JSON the consumer has received. Notice how the consumer seamlessly handles the old data and apply the default value for the new field. Now let's consider a scenario where schema evolution fails. Suppose we change the user ID field from an integer to a string. This is an incompatible change because data serialized with the original schema expect user ID to be an integer. When a consumer with the new schema tries to read older messages, it encounters a mismatch and throws an error. To avoid this, always ensure that your schema changes are compatible. Instead of changing existing fields, add new fields. For instance, if you need user IDs as a string, introduce a new field called user ID string while keeping the original field intact. This approach allows you to make changes without breaking older consumers. First, we have the original schema payment.avsc. It defines a payment record with three fields: user ID as an integer, amount as a float, and currency as a string. This is the schema our producer will use to serialize data. Now let's introduce a new schema, payment v2, incompatible.avsc. In this schema, the type of user ID is changed from integer to string. While this might seem like a small change, it creates a breaking incompatibility. when the consumer tries to deserialize all the messages. Next, the producer serializes data using the original schema. Notice the user ID is a number. Now the consumer app is restarted and it picked up the new schema in which user ID is a string. The consumer will use the incompatible schema to deserialize the same data. This results in an error with Avro type exception. Changing user from integer to string is a breaking change. Data serialized with the original schema does not match the expected type in the new schema. How can we fix or avoid this? Here are some best practices. Number 1. Avoid incompatible changes like changing field types. If a change is necessary, introduce a new field, user ID, string, while keeping the old field for backward compatible.